Hi students, in this video we are going to see about instruction scheduling. How the scheduling is happening in the ARM. That only we are going to see here. The time taken to execute the instruction, it's depend on the implementation of pipeline. Pipeline concept already we have learned in first module. If you take the ALU operations such as addition, subtraction and arithmetic operation, all these instructions are taking single cycle to complete the execution. And it depends on the shift value. If the shift value is immediate value, then it takes single cycle only. But if you use the register specific shift or any add, if you use register specific shift, it adds one more cycle. And if the instruction writes to the PC the address, then it takes one more cycles. So whenever the address is written to the PC, it takes two cycles. And load instructions, that loads n 32-bit words into the memory, such as load store instructions and load store multiple instructions. These instructions are taking n cycles, so n is the number of registers to be loaded. And load instructions that load 16 or 38-bit data such as LDR-B, LDR-SB, LDR-H, LDR-SH, these are taking single cycle only. And branch instructions, these are taking 3 cycles. Like that, store instructions also, it takes n cycles. It depends on the n number of registers to be stored. So the I told the instruction scheduling is depend on the implementation of pipelining. So pipelining, we can see the ARM9. If you take the ARM9 processor, it perform 5 operations in parallel. One is fetching, decoding, executing, then LS1, LS2. Fetching means the instruction will be fetched from the memory. Decoding in the sense decoding the operands, identifying operands for the instruction. ALU means executing the instruction. Then LS1, LS2, this is load store 1 and 2. Load store 1 is for 32-bit data, load store 2 is for 8-bit and 16-bit data. If there is no load store instruction for 32-bit, then there is no fourth stage. If there is no load store instruction for 8-bit or 32-bit data, then there is no fifth stage. We'll see some example. Example 1. And another thing, if an instruction requires the result of the previous instruction, then which is not available, then the processor stalls. This means it calls pipeline hazard or pipeline interlock. We'll see few examples. First example, add, there are 2 instructions. To complete these 2 instructions, processor is taking only 2 cycles. In the first cycle, processor will calculate R0 and R2. It will add R0 and R1, and it will store the result in R0. So if you are using pipeline, first add instruction will be fetched, then it will be moved to the decoding stage. During the decoding or first add instruction, the second add instruction will be fetched. So in the third cycle, the add will go to the execute stage and it will produce the result. So in the next cycle, the second add instruction can use the R0, because in second add instruction we need R0 of previous instruction also. The result of previous instruction is required here, which is ready. So there will not be any stall, there will not be any pipeline hazard. The second instruction also will be executed without any trouble. Next example, this example shows one cycle interlock caused by load instruction. We can see this load instruction. First, initially this will be fetched and it will be moved to decode stage. Then during the decoding of LDR, add instruction will be fetched. So during the decoding of add, this will be in executing stage. Okay. So executing means first processor will find the memory. So for that it needs one cycle. So to calculate, to add R2 and 4, it takes one cycle. By the time add will reach execute stage, So in this stage it needs R1 value which was not ready, because at that stage the processor has found only the memory, it has not yet moved the data from that memory to R1 register. So R1 is not yet ready, which cannot be used by our add instruction. So instruction stalls. Okay, so here pipeline hazard has occurred. So add instruction should wait for one cycle for earlier instruction to make the R1 ready. If R1 is ready, then add instruction will use the R1 so that it can add content of R0 and R1. So because of this earlier instruction, add instruction will wait for one cycle. Okay. So this is how one cycle interlock occurred here. Another instruction, another example, there are 4 instructions. There are few instructions. We have branch instruction also. So we have seen that branch instruction it will take 3 cycles totally. We will see how it is taking 3 cycles. See, initially we have move instruction that will be fetched and it will be moved to decode. So during then it will be moved to execute stage. So move will be in execute stage. By the time decode stage we can have branch instruction. In fetch stage we can have add instruction. Okay. So move will be completed within one cycle. Move will be completed within one cycle. Then branch will take 3 cycles. In the first cycle, processor will find the target address. Then this target address should be moved to PC. So means PC program counter should be refilled. This refilling will take 2 cycles. Totally branch instruction is taking 3 cycles. So because of this sub instruction should wait for 2 cycles. Okay. So once the target address is refilled in the PC, it will go to that location, target location case 1, and it will execute the sub. So this is how the 2 cycles are wasted here. Okay. So these are about instruction scheduling. Thank you.